The third part is to do a little bit of probabilistic analysis. So we've seen some univariate analysis, maybe the histogram plots and so on and so forth, maybe some multivariate or two-dimensional plots, like for example, the correlation plot and the covariance plots, and then the 2D histograms. But now we'll do some proper probabilistic analysis. And what I'm going to do is I'm going to choose these three columns only, the glucose, BMI, and age. I'm going to drop pregnancies because I want to do it for males and females, so I don't care about pregnancies. And then the pedigree function is not something you expect any individual to have when they come to a clinic. For example, you want to measure their glucose and BMI and take their age. Nobody was going to know their pedigree function. So just keep it out and only use these three variables, glucose, BMI, and age, with the outcome. And what I'm going to do here is we're going to use, in fact, let me just plot the data quickly. If I plot the data, this will look nice because it's a 3D plot, quite interactive. And as you can see, the red dots are non-diabetic individuals, the blue dots are diabetic individuals, and it's hard to separate. Any angle you look at the data, it's difficult to separate who is diabetic and who is not, right? That's why statistics and probabilities are quite important. So just have a pair plot of our diabetic individuals. I've seen this before in the scatter matrix, but just now separated now, the diabetics alone and diabetics alone. And we always want data to follow this bell shape. So the age now is a bit problematic. We can probably pre-process it and do some transformation so it becomes more well-behaved like this one. But again, remember, we don't have much data. Normally, you're looking at thousands of individuals to have a good estimate, but this is only like 500 or something after we've done the cleanup, which is not really a large number of data points. But what we're going to do now, we're going to fit what we call a multivariate normal distribution to our data. It's multivariate because we want to take all the variables together. So this will capture the correlations between the variables and the correlation between them and the outcome variable, right? So the glucose, BMI, and age. Remember, this is a multivariate normal model, okay? Again, this is statistical. We can explain this in more detail maybe in another tutorial or another webinar. And the way we're going to do it is, so we've split our data here in this code. Go back up quick. I've split the data here into two tables now, or two sub-data sets. One for the diabetic individuals, which is DFY, that's for yes, and one for the non-diabetic individual, that's DF no. So now we have two separate sub-data sets for each type of individual, or for diabetic or non-diabetic. In fact, let me just count how many values we have in there. So for the DFY, we have 177 individuals. For the DF no, we have 355, so almost double. You can see now the number of individuals who don't have diabetic in this data set is probably double the number of people who don't have, or who have diabetes. So remember this, because this is useful in the analysis. So now what I'm going to do is I'm going to plot my data, the same 3D plot we had here, the same plot here. But now I'm going to have a random person, which is this point here. I'm assuming that we have a random person who just walked in, we measured their glucose, BMI, and we took their age, and these are the values: 110 for BMI, 110 for glucose, 35 for BMI, 52 for the age. Let me plot it with the other data and see where it actually lands. So the red individuals here are non-diabetic, the blue are diabetic, and this green dot, the green point, as you can see here, is this random person now. So if I ask you, do you think that green dot should belong to the red, i.e. that's a non-diabetic person, or to the blue, i.e. that's a diabetic person? I bet you're going to say it's difficult to tell unless you're a real expert. But it's really difficult to tell whether that individual is, even if I zoom in and zoom out, it's really difficult to tell if that person is diabetic or not, right? It's right in the middle in there. It's difficult. And this is why statistical analysis is useful. And this is what I'm going to do here is I'm going to compute the mean and the covariance for the two data frames, for the two data sets for individuals who are healthy and individuals who are diabetic, and then fit a multivariate probability density function. That's what we call it, a PDF function that models the probabilities of my data according to the values I give it. So I give it the mean, and the covariance of each subdata set, and it gives me a nice model that can help me make predictions. So let's do it for the two of them. And whilst I'm modeling, this is what this code does. Whilst I'm doing the modeling, after I fit this multivariate model to my data, I try to predict the test point. Okay, I say, give me the probability of that test point, which is this, with these values, give me the probability of that test point belonging to the diabetic group, and then give me the probability of that test point belonging to the non-diabetic group. If I run that, and now, please pay attention to this. This is a mistake that a lot of people do. If you remember, we checked the number of individuals in the diabetic group and non-diabetic group, and we said that it's almost double in the non-diabetic group. What that means is our data is not really balanced. We're always looking for data with the same number of individuals, or close, at least approximately the same. In our case, it's not. So we need to calibrate or calibrate or weigh the probabilities, meaning we need to use the size of our data into the equation. So now we've got the raw probabilities, and what I do here is I take, for example, the probability of, so let me show you what this array now looks like. It will have two values. The first value is for the yes data. So this value here is the probability is 4.8 times 10 to the minus 6. So it's a very small number. And this is again 2.4 times 10 to the power of minus 6. So it's a very small number. This tells me this is the probability of that test point belonging to the yes data to the diabetic individuals. This value here tells me this is the probability of this test point belonging to the no individual, to the ones who do not have diabetes. But these are not now put against each other, because each of them is derived from a different set of data points, different set of individuals. Okay, and now to put them together, I need to have the size of the data in mind. That's why what I do here is I take the first value, which is the probability of belonging to the diabetic individuals, multiply it by the number of diabetic individuals I have, and then I divide by the same value multiplied by the number of diabetic values, plus the probability of the point belonging to the non-diabetic individuals multiplied by the number of non-diabetic individuals. That num n, and num yes is number of diabetic individuals, num n is number of non-diabetic individuals, and I do the calibration. And when I make those computations, my statistical model tells me that there's a 49.62% chance of that point belonging to the diabetic group. So it's less than 50% probability or chance of being diabetes, and slightly more chance, 50-point-something% chance of it belonging to a non-diabetic group. You see, I told you it's very difficult to tell, and that's confirmed by the probabilities. It's very close. Okay, we don't have a clear-cut opinion here. If we use the 50% as our threshold to decide, then okay, we might go, it's okay, it's not diabetic, but at the same time, remember that the probability of being diabetic is very, very high. It's very close. Okay, so of non-diabetic now, if I do it the other way around, if we do the n, which is negative now, which is non-diabetic of negative, you will notice it's very close. Okay, it's 50 points something, really close. And that's difficult to decide now because the probabilities are close. So always remember, should always pay attention to this weighting issue when we do the probability, especially when the data is not balanced, and the weighting is quite important, and so on and so forth. Now the fourth part of my, let me have a quick look at what I've written here quickly. So we normally don't directly compare the distributions because the number of instances is different, like we said, and always remember probabilities need to sum up to 1, and always remember the issue of weighting. So this actually ends the third part of my seminar or my webinar, and the fourth part is about using the logistic regression model to model our data and make these predictions.